Welcome to CS70 Spring 2018 Discussion 11B. We're going to talk now about problem 1, which talks about a linear transformation about a Gaussian random variable. So the problem setup is as follows. We have x, which is normally distributed with some mean, mu, and some variance, sigma squared. We construct a new random variable, y, which is some linear transformation of x, i.e. it is some ax plus b. We now have to comment on what the distribution of capital Y is. So before we talk about the explicit distribution, let's talk about some easier things to compute. First, let's talk about the expectation of y. Well, this is going to be the expectation of a times x plus b. And by linearity of expectation, we can write this out as a times expectation of x plus the constant b. Finally, e of x we know is mu. So this thing becomes a times mu plus b. All right, that was not so hard. Now let's talk about the variance of y. Once again, this is the variance of a times x plus b. Now we know adding a constant to a random variable does not change the variance. So this is the same thing as the variance of a times x. And finally, scaling reflects with a square factor. So this is a square times the variance of x. And finally, we know that the variance of x is sigma squared. So first we conclude that e of y is a times e of x plus b, and the variance of y is a squared sigma squared. Now what's amazing is not only are these things true, but y follows a normal distribution with these parameters. So let's go ahead and prove that. Okay, well, we know that the normal distribution has this complicated looking PDF right about here. However, what we don't know is the CDF of the normal distribution in an explicit form. However, I can abstractly represent it. So what I mean is this quantity, capital F for x, which is defined as this integral, I do not have an explicit formula for this. However, by definition, I know that this is the probability that x is less than or equal to some little x. Okay, and the question is, can I relate y to this thing? So what I'll talk about is the CDF of y, which is defined to be the probability that capital Y is less than or equal to some little y, right? Now this thing is the same as the probability that a times capital X plus b is less than or equal to some little y, which is the same as ax being less than or equal to y minus b. Now at this point, you're wondering, why did I just subtract b and not divide by a as well? The thing here is I need to take two separate cases of the case when a is positive and the case when a is negative. Why do I need to do this? Well, if a is negative and I divide by a, this inequality over here flips. Remember, multiplying and dividing by negative numbers flips inequalities. In the case that a is positive, nothing bad happens, which means this thing is equal to the probability x is less than or equal to y minus b over a. The discussion solutions talk about what happens here, so let me talk about what happens here. So in this case, this is equal to the probability that x is greater than or equal to y minus b over a. So I divide both sides by a and my inequality flips, which is the same as 1 minus the probability that x is less than or equal to y minus b over a, which, continuing, is, so this is just 1 minus capital F at y minus b over a. And remember, a is a negative number over here, right? So we're working in the regime when a is less than 0. OK, well, this is the CDF of y. But this didn't help me too much because I don't know an explicit formula on the right side. However, I can differentiate both sides with respect to y. And you get that the derivative here of this thing is equal to the PDF of y, again by definition. And now differentiating the right side, I get negative the PDF of x evaluated at y minus b over a times 1 over a, where the 1 over a follows from the chain rule for differentiation. Well, OK, so now I have this relationship. And remember, negative 1 over a makes it a positive number. So I can also write this equivalently as 1 over modulus of a fx at y minus b divided by a. And remember, fx refers to the Gaussian PDF over here, and that I do have an explicit form for. So let me finally go ahead and use that, where what I'm going to say is that, so starting from the fact that I now know that the PDF of y, in terms of what it is for x, is this thing. Well, this is just 1 over mod a, this formula of the PDF, but instead of x, I plug in this quantity over here. So I get 1 over root 2 pi times sigma squared times the exponential of y minus b over a minus mu squared over 2 sigma squared. OK, well, at this point, everything that I'm going to do is just algebraic manipulation. So I'm going to write mod a as square root a squared. So I will get 1 over root 2 pi a squared sigma squared times this exponential, where what I'm going to do is multiply and divide by a and then take it outside. So I get y minus b minus a times mu squared over 2 sigma squared a squared. And finally, I'm going to pattern match this to the Gaussian PDF. So I'm going to write, so I'm going to define sigma y to be a times sigma and mu y to be b plus a mu. And remember, this is exactly what we had calculated these to be at the start. So I get that my PDF is 1 over root 2 pi sigma y squared, the exponential of y minus mu sub y squared over 2 sigma y squared. Now this has the same form as a Gaussian PDF, so we conclude that in fact capital Y not only has this as the mean and this as the standard deviation, however, it is normally distributed with these parameters, sigma squared y. Thank you.